Okay, so let's draw a picture. And this time I will draw an x-axis, but I still won't draw a y-axis for the same reason as before. It just gets in the way. But let's draw the x-axis. Okay, and imagine you've got a curve that looks something like this. Okay, so where are the local extrema in this picture? Well, we've got one here. Here's a local maximum, right? And then we've got a local minimum down here. We've got, this is technically a local maximum, but probably more specifically it'd be better to describe it as an absolute maximum. And then we've got a local minimum down here. And I guess this would be an absolute minimum as well. So those are your four extrema. So let's make up some labels for the x coordinates. Let's call this C1, C2, C3, and then C4. Let's say those are the x coordinates of those four local extrema. So which one is happening? I mean, this is certainly a function that looks nice and smooth over here, right? So it looks like the function is differentiable here. It looks like f prime of C1 exists. Well, what would it be? Well, just draw a picture of what the tangent line would look like at that local maximum. What's the slope of that line? It sure looks like it's flat, right? And presumably it would be if it's right at a maximum. If the line was tilted just a little bit this way, then you probably think it needs to be moved over to the right a bit if in order to be the maximum. And if this tangent line was sloped downward, well, then that means you probably need to push the point a little bit to the left to get it to be the maximum. But if it's right at the top of that little mountain, then the tangent line is going to be flat. You can think of it as like a ruler balancing on a hill. So in that case, well, f prime of C1 is equal to 0. So how does that play into our previous statement, Fermat's theorem? Well, we've got a function. It has a local, a maximum. It's got a local maximum at C1. So take C1 to play the role of this x value. It says that if f prime of C1 exists, then f prime of C1 is going to be equal to 0. That's what you get if you apply this theorem to the point C1. And it looks like, sure, in this case it's equal to 0, so the theorem is satisfied. Same with C2. Right? If you draw a sketch of the tangent line to the graph at the point C2, I guess if I really want to be clear here, I should say that this is the graph of y equals f of x. That's if I want to really explicit my OCD symptoms. But in any event, this really is the graph of some function f. So it makes sense to call the slope of this tangent line f prime of C1, and it makes sense to call the slope of this tangent line f prime of C2. And since that's also a flat line, we know that the slope has to be 0. So f prime of C2 is equal to 0. Let me skip this one for the moment and go on to C4. It's no different, right? If I draw the tangent line to the graph at that point, C2, or pardon me, C4, it's going to be flat because it's right at the bottom of that valley. So in this case, f prime of C4 is also equal to 0. But there's other ways that functions can have local extrema, right? Look at this one. Is the slope of the tangent line there going to be equal to 0? Can you even draw a tangent line at that point? No, because the function is not differentiable at C3. So you're unable to draw a tangent line there. You could draw lines that only touch the curve at a point, but they're not going to be tangent lines, right? Because tangent lines by their very nature are unique. So I mean, I could draw a line that goes through that point like this, I could draw this line, or I could draw a flat line, I could draw a vertical line, right? None of those are tangent lines. So in this case, f prime of C3 does not exist. In other words, f is not differentiable at C3. So that's just a picture of really what Fermat's theorem is telling you. It's telling you that if you want to find the local max and local mins of a function, look for places where the derivative either doesn't exist, places like that, or look for the places where the derivative is equal to 0. That's how you can find the places, or the x values, where local maxes and local mins occur. So because of this phenomenon, we're really interested in those values. We're interested in values C that make a function either have a zero derivative or make its derivative undefined. So that's what the purpose is of this next definition. So here it is, a number C in the domain of f. That's actually an important requirement. We're talking about numbers that are actually in the domain of the function in question. So if you have a number in the domain of a function f that satisfies the two conditions that we're going to write down in a moment, then it's called a critical number. So what are the two conditions? And it's if either of the two conditions hold. So it's not, you don't have to satisfy both of these conditions. In fact, you will once you see them, you'll realize you can't satisfy both of these conditions. You can just satisfy one or the other. But if either of these two statements are true, then we say that C is a critical number of f. So the first statement is just f prime of C is equal to 0. And the other statement is f prime of C is undefined. So if either of those statements are true, then C is called a critical number of f. And I like to give them names because I find it's useful when you're using critical numbers. It's useful for distinguishing between which one of these statements is true. So I like to call these type 1. So a type 1 critical number is a number C in the domain of a function by virtue of the first statement being true. So it's a type 1 critical number of a function f is a number in its domain, a number C in its domain, such that f prime of C is equal to 0. And then a type 2 critical number, C of a function f, is a number in its domain such that f prime of C is undefined. So I just find it, I said 2 and I wrote 1, so let's make that 2. That's type 2 critical numbers. Okay, so let's look at an example. And then we can find all the critical numbers, both of type 1 and type 2 of a given function. So here we've got an example which asks us to do exactly that. And the function in question here is f of x is equal to x to the 3/5 multiplied by 4 minus x. So let's go ahead and find the critical numbers. How are we going to start? Well, the definition of critical number kind of tells you what you need, right? If the definition of critical number was involved the derivative of the function, we're probably going to need the derivative, right? So let's start by finding f prime of x. So f prime of x, and we can use the product rule. That's one way to take the derivative here. It's not the only way, but that's what I'll go ahead and do. So the derivative of this function using the product rule, we're going to get the derivative of x to the 3/5 times 4 minus x plus x to the 3/5 times the derivative of 4 minus x. Okay, so what happens if you differentiate x to the 3/5 using the power rule? You're going to get 3/5 times x to the 3/5 minus 1 is negative 2/5. So that'll be multiplied by 4 minus x. And then over here, we're going to have, this will be just x to the 3/5 multiplied by negative 1. Okay, so that is what you end up getting. That's your derivative. But so when's that 0? For what values of x is that equal to 0? And you're probably thinking that that's not really in the most convenient form to tell that or to answer that question, right? It's not easy to just look at this and decide, well, for what values of x is this equal to 0? And for what values of x is it undefined? So this is where you're going to want to make it a habit to simplify things. And typically what that's going to look like for these types of examples is you're going to want to write everything as a single fraction. So start right off the bat, make these negative exponents, write them as positive exponents in the denominator. Let's start with that. So the first step, after differentiating, we'll write this as 3 times 4 minus x over 5x to the 2/5. So that's what this first term looks like if you change this negative exponent to a positive exponent. And then the second term, we just got minus x to the 3/5. Okay, well, now what? Well, we've got a fraction minus some other expression that's not a fraction. Why don't we get a common denominator and write it as a single fraction? So let's just multiply this second term by 5x to the 2/5 divided by 5x to the 2/5. All right, so what happens? Well, this term is not going to change, but this term is going to become a fraction with a denominator of 5x to the 2/5 like we want. So you're going to get, I'll just write it out in detail. So 3 times 4 minus x over 5x to the 2/5. So first term didn't change. Then we're going to have minus 5x divided by 5x to the 2/5. All right, so good. We got a common denominator here, right? We can actually just say this is going to be equal to 3 times 4 minus x minus 5x all over 5x to the 2 over 5. And now we can just clean up the numerator. So let's multiply the 3 into the brackets. So we'll get 12 minus 3x minus 5x all over 5x to the 2/5. And then we can combine our like terms finally to write this as 12 minus 8x all over 5x to the 2/5. So now, when you want to find your critical numbers, remember we're looking for places where the derivative is either equal to 0 or the derivative is undefined. So if you've written your derivative as a fraction like this, a single fraction, then it's straightforward to do that. If you want to find the type 1 critical numbers, set the numerator equal to 0. And if you want to find the type 2 critical numbers, set the denominator, 5x to the 2 over 5, set that equal to 0. Okay, so let's do that and just look at when that's going to happen. So I'll keep going with this pen. So 12 minus 8x is equal to 0. That's going to happen. Well, you can solve that for x, and you're going to end up getting 8x is equal to 12. Right? If you bring the 8x over to the other side, you'll get 8x is equal to 12. Divide both sides by 8, and you'll get x is equal to 12 over 8, which reduces to 3/2. So you'll get when x is equal to 3/2. So that is your type 1 critical number. X equals 3/2. For type 2, let's put it up here. There's room. For your type 2 critical numbers, well, you're going to just set the denominator equal to 0. When is, because that's what makes the derivative undefined, right? If the denominator is equal to 0, then the fraction is undefined, and therefore the derivative is undefined. So that's why for the type 2 critical numbers, if you've got a fraction for your derivative, just look for places where the denominator is 0. Okay, so, well, when is 5x to the 2/5 equal to 0? Well, that's going to happen when, well, divide both sides by 5, and you're going to get x to the 2/5 is equal to 0. Right? And any power of x is going to be, any positive power of x is going to be equal to 0 exactly when x is equal to 0. So for something like this, this is going to be true when x is equal to 0. Okay, so that's the details for finding your type 2 critical number. And this is the details for finding your type 1 critical number. And since we were asked for critical numbers in general, we want both. So let's put our final answer like this. Our critical numbers, I'll just abbreviate number with a pound sign. Do we want x equals 0 and 3/2? Okay, so that is how you can find the critical numbers of a function. Now this example doesn't show you what you're going to do with those critical numbers, and that's coming up next. But for now, this just shows you how to find the critical numbers. Okay, one last comment. By Fermat's, or pardon me, by the virtue of the fact that absolute extrema are automatically local extrema, we can really just formulate our goal as we're just looking to find local extrema, right? Because if we find all the local extrema, then we will by default have found the absolute extrema as well, since they are themselves local extrema. So, and Fermat's theorem tells us that critical numbers are going to tell us where local extrema happen. Right? Critical numbers, we didn't define them until after Fermat's theorem, but if you could now restate Fermat's theorem in terms of critical numbers, and Fermat's theorem is basically telling you that that's where local extrema are going to happen. They're going to happen at critical numbers. So putting those facts together, that tells you how to find local extrema and how to find absolute extrema as well. Just first find the critical numbers, and then figure out what the values of the function is at those critical numbers, and then we can compare them. So that's going to give us enough tools to actually write down what's called the closed interval method, which is coming up next.